Hi, welcome to the video on losses and power flow diagram of DC motor. To begin with, there are three types of losses in DC motor, that is copper loss, iron or core losses and mechanical losses. When it comes to copper loss, it is taking place due to the current flowing in a winding. There are basically two windings, armature winding and field winding. If you go through the video which is made on types of DC motor, you can see what type of windings would be there in DC motor. So these two windings, that is armature winding and field winding, the copper losses are proportional to the square of the current flowing through this winding, that is the armature current. Therefore, if you observe here, copper loss is I square R. That is, with respect to armature, it is Ia square Ra. With respect to shunt field, it is the current flowing in the shunt, that is ISH square of RSH. And when it comes to series, it is ISC square of RSC. In a compound DC machine, there exists brush contact resistance drop and is included in the armature copper loss. So when it comes to iron or core losses, it is also referred as magnetic losses. This includes hysteresis losses and eddy current losses. Hysteresis losses is given by the equation eta Bm to the power of 1.6 Fv. It is proportional to the frequency and the maximum flux density Bm in the air gap. This loss is basically due to reversal of magnetization of the armature core. This eta is Steinmetz constant, where V is the volume of core in meter cube and F is the frequency of magnetic reversal. Now coming to the eddy current loss, it is given by K Bm square F square T square V, where K is constant and T is the thickness of each lamination and V refers as usual the volume of the core. It is due to the eddy currents. When the armature core rotates, it cuts the magnetic flux and EMF gets induced in the core. This EMF induced will set up a eddy current which causes the power loss, that is eddy current losses. Now coming to the mechanical losses. It consists of friction and windage losses. So some power is required to overcome mechanical friction and wind resistance at the shaft. This loss is nothing but the friction and windage losses. These losses are constant for a DC machine. So the magnetic and mechanical losses together are called as stray losses. So the magnetic, that is iron, and mechanical losses together put, they are called as stray losses. For a shunt and compound DC machines where field current is constant, field copper losses are also constant. The stray losses along with constant field copper loss are constant. Armature current is independent on the load and thus armature copper losses are also called as variable losses because it varies with respect to load. Thus for a DC machine, total losses will result in constant losses plus variable losses. So these are the flowchart of the losses which is discussed so far in the video. Where we have two major losses, constant losses, we have no load iron losses and mechanical losses. No load depends on hysteresis and eddy current losses, where mechanical losses further classified as windage and friction, and together these two constitute a stray losses. So variable losses is copper losses, that is I square R, and stray load losses also, which are variable with respect to load. So under copper losses we have stator copper losses, rotor copper losses and brush contact loss. Under stray load we have copper and core stray load losses. Now efficiency of a DC machine. In case of a DC motor, the following three efficiency are defined, or for shunt machines and series machine. If you take a efficiency, it is P output by P input. When for maximum efficiency, we have a condition for maximum efficiency where Pi, the iron losses, will be equal to copper losses. So in case of a DC motor or DC generator, the condition of maximum efficiency remains same, where The maximum efficiency occurs when Pi is equal to PCO. So considering this condition, if you derive the equation for Ia for shunt and series machine, the load current Ia is given by square root of Pi by Ra, and for series Ia is equal to Pi by Ra plus Rsc. Now coming to the power flow diagram, as a DC motor and as a DC generator, if you look at, for a DC motor, efficiency is P output by P mechanical. So if you look at this, the output is mechanical and input is electrical, so that defines the efficiency. But in between this, the stages of power flow will is goes like this. So for a given input electrical power, if you observe, we have a power input to armature, that is PA, and then we have power input to the field, and then we have the power, gross power developed by the armature is given to the core, and then we have a losses, then we have a mechanical output here. If you see the DC generator, we have a mechanical power input and the electrical power output. So the gross power developed by armature, we have a mechanical losses and we have a copper losses here, core losses here. So this goes the power flow diagram of a DC machine. So in between, as I said, between this electrical power developed in the armature and input of electrical power, we have iron and friction losses, and then between electrical power developed and electrical power output, we have copper losses in between for a generator. If you look at the DC motor, it is reverse. So first occurs for copper losses in between the input and power developed in mechanical armature, and the losses, that is iron and friction losses, is developed between the motor output and the power developed in armature. So this is how the power flow diagram works for DC motor and generator. Thank you for watching this video.